Hello and welcome to the 8th lecture of Machine Learning for Robotics and Computer Vision. In this lecture we will talk about how to actually learn convolutional neural networks. But first a short recap of what happened in the last lecture. In the last lecture we talked about building blocks for convolutional neural networks, which were essentially the convolutions, max pooling and fully connected layers. And we also talked about that these specifically then excelled at the ImageNet 2012 competition and really showed that convolutional neural networks are a method to actually achieve very good results on this very challenging data set. Now the question is, we had this convolutional blocks which had many parameters for the actual convolutions. How do we actually learn these parameters? So here just a small example. We have this car image and we have some convolutional blocks here shown in blue, and we have then the fully connected layer in the end that returns our score values in the end. For this example we have 10 classes, so this dimension is then 10, and by using a softmax we can then turn this into a probability distribution. And in this case here you can see that the class is wrongly predicted as truck. So what we want to achieve is basically take the parameter values of the convolutions that produce the output of the convolutional layer and maybe use the W1 and want to modify it in such a way that we are getting then hopefully in the end the correct class, which would be in this case automobile. And the question is now, how do we measure actually if we are doing the correct change in the end? And this comes then to the so-called loss functions, which basically measure the difference between the predicted outcome and the desired outcome in the end, which would be in this case desired outcome, of course, automobile, and our prediction is then shown here by this probability distribution. So what it boils down is to that we want to have a loss minimization in the end. So the loss, which is a scalar value in the end, determines the difference between our prediction. So we are now taking here the view that the convolutional neural network is just a function of its input xi and the parameter theta and the target value yi that we want to have. And the loss over the whole data set is then given by the average over the individual losses for each example. So this is an important thing that we also later will exploit for optimizing that in the end, that the overall loss over the whole data set decomposes in the losses for each example. And typical loss functions that we can use are then the so-called L2 loss for regression and the cross-entropy loss. So the L2 loss is defined by just the difference between the target value, which is now a scalar, and the predicted value, which is the outcome of the convolutional network in the end. And this is then squared. And intuitively we want to get the output values of our function as close as possible to the target values. And the farther away we are getting from this target value, the higher the loss will be that we are incurring. And this is, when you remember, when we talked about regression in a regression lecture, this is then equivalent to the negative log likelihood with a normal distributed error, as we had for the linear regression in the end. So, and of course this loss function is then also implemented in PyTorch, and that's called the MSE loss for the mean squared error. And coming to the classification loss, for classification we are using very often just the cross-entropy loss. And as we before, for classification we are turning the score values that we are getting back from the network, which is here then f1 of x to fc of x, into a probability distribution by just using the softmax function. And when we are using, as before, the negative log likelihood of the softmax function, we are then getting our loss in the end. So which is then minus log of the softmax function, and when we are then pushing the logarithm in, then we are getting then minus of the output of the correct class, which would be in this case j, plus the logarithm over the sum over all scores. And this is then the loss. So we are now talked about the negative log likelihood of the softmax function, and then the question that naturally arises is, why is this then called the cross entropy loss in the end? And for the cross entropy, we have the cross entropy defined over probability distributions P and Q, and we are summing over individual entries of the probability distributions. And the cross entropy basically encodes the difference between P and Q. So this will be 0 when P and Q is equal in the end. For our target label J, we are now encoding the probability distribution as the one hot vector encoding. So all the entries for all other classes are basically 0. And for the Jth entry, we are just putting a 1 there. And for the Q distribution, we are just using the softmax as before for the Q. So that we have the softmax of F1 to Fc, and we then, when we are putting this back into the definition of the cross entropy, then you will see, because we have just this one entry in the P of x, we are then just getting -1 of logarithm of Q of x, J basically, because this is the only part that is left. The other parts are just 0. And then, as it turns out, this gives then exactly the same expression that we had by using the negative log likelihood on the softmax function. And so therefore you see here the relation to the cross entropy. Where it gets interesting is when we are not using just a 1 at a specific position in this P, but we can use also other distributions. So we can maybe encode our uncertainty about the label, so that we are not having a 1 there, but maybe a 0.9, and for some other class a different value, such that it sums up in the end to 1. So of course this is then also implemented in PyTorch, so there it's called the cross entropy loss. And as you can see on the bottom of the slide, you will see then also that there it's exactly the same as said. So, and in the beginning it's also said that this is basically just the combination of the log of the softmax loss function and the negative log likelihood loss. So, and the advantage of using the implementation of the cross entropy like this is that it accounts for the things that we also discussed when using the softmax function, so that we are basically getting a more stable result in the end. So we now have loss functions defined on the output of our CNNs, which encode basically where we want to go. So we want to minimize the loss in the end. And for minimizing the loss, we are of course back at using gradient descent. So we are using a gradient-based optimization. So for a specific parameter, in this case W1, we want to determine the partial derivative of the loss in respect to W1, and want to go in a negative gradient direction. And by using this, we then can optimize the individual parameters in a way that we are minimizing the loss in the end. So in this example here, I plotted basically the loss for a specific W, but you can think of that you can do this also for all other W's at the same time. And there we are talking about the gradient direction, because we have then multiple W's, and this is then a vector basically on the loss surface, and we want to reach basically a minimum on this loss surface. And the partial derivatives tells us basically in which direction we have to go, or which direction we have to change the W's in the end, such that we are getting the loss minimized. And for computing the partial derivatives, we can now apply the so-called chain rule. So you can, as I said in the last lecture, when you're thinking of neural networks, it's basically just a combination or a composition of functions in the end. So that means we have f of f1 of x, which gives us an output, which is then put into f2 with its own parameters, theta2, and then the output of this is then put again into a function f3, and this is then the result in the end. And to compute the partial derivatives now, we want to compute basically the partial derivative of L in respect to the individual thetas. We can now apply the chain rule. So for computing the partial derivative of L in respect to theta 3, we are just using the chain rule to get the output of the partial derivative in the end. So in this case, it's L in respect to f3, and then we are having the f3 in respect to theta 3. So we are taking the outer function and then multiply it by the partial derivative of the inner function. In the case of theta 2, this gets then a little bit more interesting, where we have our L and we are doing the partial derivative in respect to f3, and then we have f3 in respect to f2, and then we have the partial derivative of f2 in respect to theta 2. So it's just a multiplication of basically the f3 is then the output in respect to its input, f2, and the partial derivative of 2 in respect to its parameters, theta 2. And then we can do the same for theta 1. So we are starting again with the base case, which is L in respect to f3. We are doing then the partial derivative of f3 in respect to its input, f2. And then we are doing the same then for f2 with respect to f1. And then we are reaching basically the base case again, or the local gradient, where we have f1 in respect to theta 1. And when you look at the formulas, you will see a pattern arising here, that in each step we basically have only to compute a part of this expression. The other parts of the chain rule we can just reuse from before. And the interesting part is now, when we are writing this up, basically, we can see the order of the operations. But we have now to tell the computer basically how is the order of the operations defined to do this in the end for us. And therefore, how do we determine the order of the computations? And for this, the concept of the compute graph is introduced. So each algebraic operation, in this case it's f of x, y, and z, which is defined by the sum over x and y multiplied by z, can be then transformed in a computational graph. So we have our inputs x, y, and z, and have now directed edges to the compute nodes to tell, okay, these are the inputs of the plus operation in the end. And q is in this case the output of this plus operation, and as written here, it's then q equals to x plus 1. So this node will give us then q as output in the end. And then we have now computed the expression in the bracket. We can then use this expression in the next part to define the multiplication, which is then just taking the result of this compute node q and multiplies it by z, which gives us the desired output f in the end. And the important part is here that the edges in this directed graph determine also the information flow in the end. So x and y flows into the plus computation node, and then the output of this goes into the multiplication node, and then we have the input z which then will turn out to be the result f in the end, what we want to have. And using this compute graph, we can now determine in which order we have to apply operations, but we have also can determine in which order or which direction we have to compute the partial derivatives in the end for our chain rule. For a given input, we are now computing first the outputs. So in this case, we have as inputs for x3, for y4, and for z -2. And then we are just applying the directions of the edges and using this then to determine the outputs. So for q, this is of course then the sum of 3 and 4, this is 7. And for the product of 7 and -2, this of course is then -14. So in this representation as shown here, the output of the compute nodes, or what goes in basically, is always above the edges. And when we are now want to compute basically the partial derivatives, in this case we want to compute the partial derivatives of x, y, and z, we can use this graph then to do the backward pass over the graph. And this backward pass then defines the order in which direction we are doing the chain rule in the end. And in the backward pass, we use the chain rule to compute then the partial derivatives. And important is here that we then also can reuse the already calculated derivatives, but also already computed activations, which we had in the end. And for the backward pass, this looks now like this. So we have the graph again, and we are starting now at the end, in this case here. And we first want to compute the base case, where we want to have the derivative of the output in respect to its input. And as you might remember, the thing that we want to have here is then how much does f change when we are changing f. And in this case, this is simple because f, of course, changes in the way that when we increase f, then f will, of course, increase also by 1 in the end. So therefore, the partial derivative of f in respect to f is, of course, 1 in this case. When we now then go to the more interesting cases, so when we want to compute next the partial derivative of z, we go along the graph and then have to see what are basically the inputs here. And we want to compute here the partial derivative of f in respect to z. And as this is defined as the product of q and z, then you might remember from calculus the partial derivative of f in respect to z is then just q in the end. And so we can now look up in our computation graph, which we computed before. We can take this value and just copy it there in this case. So the partial derivative in respect to z is then just q, and this q is then the 7 that we computed before. And this was also quite easy. The same we can do then also for q. And here we can see that the partial derivative in respect to q is then just using this function again, is then just z in the end. So we are copying basically the value from z here to this part, it's -2. More interesting it now gets when we are coming to the part where we have now the output of a function that is not directly influenced by the, or where we have this composition of different functions. And this is now the next case we want to compute. It's basically the partial derivative of f in respect to x. And here we have to apply the chain rule. So, and this looks then as follows. So we want to have the partial derivative of f in respect to x. So that means we first do the partial derivative of f in respect to q and multiply it by the partial derivative of q in respect to x. So, and as shown here, the partial derivative of f in respect to q we already computed. This is -2. And the partial derivative of q in respect to x. So as remember here that q equals to the sum of x and y. And we do the partial derivative in respect to x, and this is just 1 in the end. So that means to compute it, we have then 1 times -2. So the partial derivative of f in respect to x is then just -2. And the same derivation we can basically use then for y. The only thing that changes is here the denominator, which is then not x but y in this case. And as q is the sum, when we apply there the partial derivative, then we just have a 1 again here. So we have -2 also here. So, and with this we are basically at the end, and we computed all the partial derivatives for the variables that we were interested in. And as you might have noticed, when we talked about the derivation also of the chain rule, we just looked at the local information here. So that means for calculating the partial derivative for f in respect to y, we are just taking into account the output here, so d of f given q, and the functional form of the compute operation. So, and this is an interesting fact here that we can exploit, that we have just to account for the local connectivity of the compute nodes. For each compute node, we are only interested in what goes in and what goes out in the end. So, and you can think of it like, yeah, passing messages around. So in the forward pass, we are computing the functional value of x and y, which go in, and then we are communicating a message with this activation to the graph. And then no matter what happens behind it, what we are only interested in is basically then the message that comes back. And this message is then basically the partial derivative of the function that we want to compute the partial derivative for. In this case it's L, and in respect to the output that we computed before. And this is then the information that we need to then compute together with the local gradients. So we have here the partial derivative of the output in respect to its inputs. So we have the partial derivative of that given the partial derivative of x, and the partial derivative of that given the in respect to y. And then we can use the so-called upstream gradient with the local gradient together to compute with the chain rule then the message that we are passing on to the graph again, which is then the downstream gradient in the case, which is then using the chain rule. So, and this is then happening all over the graph, and it's here the interesting part is this is a very local thing. So no matter what happens here and what happens downstream the graph, this not influences at all how we compute the gradients here. And until now we just computed the partial derivative for scalar value functions, but of course we can do this also for vector value function. And when you remember this from calculus, for a function that has a vector as input and a scalar as output, then the derivative of the function in respect to x is then a vector. And in this case, we are taking here column vectors as the gradient vectors, because this has then the advantage that we can just apply this gradient vector to our weights or something like this. And then using this representation as column vectors, we can also have then functions that take in a vector and output a vector. And for this, the Jacobian is basically the derivative that we have. So, and important to note is here that the Jacobian is a matrix of dimension m times n. So we have the the number of rows is the number of output values that we have, and the number of columns is basically the input values. So that means when we are thinking of the gradient, we have the gradient for each function f as the transpose of this column vector here. So the first function, then the second function until the mth function, and we have in each entry the partial derivative of this specific function f1 to fm in respect to the variables, in this case xn. So we have, and this will be important when we are now talking about the actual how we apply basically then the backpropagation with vectors. And when we are talking about this, we have to talk about a little bit about the dimensions. So as before, we have the same view on this compute node. So we're getting the upstream gradients, we have the local Jacobians in this case then, which are matrices, and then we have here the output, which is then the matrix vector multiplication. So we are computing again x and y. This is then, in this case, when we use a function where we have inputs, two inputs, this looks then like this. So for the first input we are using a dx dimensional vector, and for the second input the y dimensional vector, and the output is then a dz dimensional vector. And we are talking now about the dimension of the vectors. Then of course the dimension of the x vector is dx, and the dimension of the y vector is dy, and then the output of the function is then just a vector of dimension dz. And as before, with the message passing analogy, we are producing a message that is a dz dimensional vector, and we are getting back also a dz dimensional vector, which is then the gradient of the function L in respect to z. Then we are computing the Jacobians, which are then, as you remember, has dz rows and dx columns. And for the function of z in respect to x, and for z in respect to y, we have dz times dy. And to make now sense of the chain rule, this is also something that you maybe noticed. We inverted here the order of the operations, so that usually we talked about that we are having the function that we want to derive, and then we are having dz times the partial derivative of z in respect to x. And we inverted this to make also sense of the matrix multiplication. And in this case, to have a proper matrix multiplication, so when we have this matrix times this vector, this will not work out because the dimension of dx doesn't maybe not match the dimension of dz. And therefore we are using here the transpose of the Jacobian. So this is just a design decision in the end. So because we said that the gradient vectors are column vectors in the end, we have to do, in this case, the transpose of the Jacobian to get a proper matrix vector product. When we would have decided differently and said like the gradients are row vectors, then we could just use the matrix product in the case that we are just using the row vector times the matrix. But it's just an internal thing. So also for the exercises, you have to note that this Jacobian that you're maybe computing there has to be transposed in the end to make a proper matrix vector product in the end. Coming now to a short example, how this then looks like for a real node in the end, or compute node. In this case, it's the ReLO activation, as you might remember. The ReLO activation just takes the maximum of 0 and x, so the element-wise maximum of 0 and x. And when we have in this example now here as input 1, -2, and 3, then the element-wise maximum will then return 1, 0, and 3. And this is then the output, and then, as I said, we are passing on the message to the rest of the graph. Then some operations happen, and then we are getting a message back, which is then the gradient of the output function that we want to have in respect to y. And this is then, in this case, for instance, minus 1, 4, 2, which which has nothing to do with this 1, 0, 3, because there are some other operations happening. This is just a value that comes back, which I just choose here in this case. And then using this, we have then the upstream gradient. We are computing the Jacobian of y in respect to x. And as the maximum function is here used, we have just a diagonal matrix where all the entries are 0 for the rest of the numbers. But here this is because this returns 0 in the end, so we have here the gradient of 0. So and using this we can then compute the transpose of this times this matrix, this vector, and then we get back the desired partial derivative of L in respect to the vector x, which is then the gradient vector minus 1, 0, 2. And as you can notice now, basically, when we have an output of 0 here, then basically the gradient in this direction is basically blocked in the end, because the gradient for this specific direction is then 0 in the end. So, and computing the explicit Jacobian, for instance, for this ReLU activation is maybe a little bit too costly in the end, because when we are thinking here of images, then we maybe have a very high dimensional vectors that we have there in the end, and computing therefore the explicit Jacobian would take a lot of space in the end. And therefore what usually happens in this compute node analogy is that we can basically, we know how the function should be computed, then we can use this knowledge to basically compute also the output of the backward pass in the end. So, and here it just depends on the input value that we have. If the input value is larger than 0, we are just copying basically the upstream gradient entry in this case. So this would be minus 1 and 2, because here the input values are larger than 0. And for the other value, we are just returning 0. So in this case, because this x2 is minus 2, we are just copying this, we are just returning 0 in this end. And therefore, we can efficiently implement this in this case. And this whole analogy of doing a forward pass and backward pass is, of course, then also reflected in PyTorch, where we then have functions that explicitly encode this forward function, where we are just computing, in this case, for this multiply operations, the product of the inputs x and y. And for the backward pass, we have basically to save the activation values, because we will then need them in the end. So therefore, we are storing this. And then in the backward pass, we are just using this saved x and y. And then we can compute the chain rule for computing the gradients, and then return in the same order as we had the inputs x and y, also the gradients for x and y. So nothing to be afraid of here in the end. So the only thing that you might notice is, for doing the backpropagation, we have always to store basically the activations. And this has maybe the restriction or the problem that we, while training, have to not only compute the activations, but to store them, to then compute also in the backward pass the gradients. And therefore, we have not only the weights that we have to store, but we have also to store basically the paths that we need to then compute the outputs in the end. And therefore, usually this increases the size of the memory size of the network while training. And for this, we can basically exploit that we don't want to compute maybe all or store all activations in the end. And there's this concept of gradient checkpointing, where we only store basically the heavy forward passes in the end. So where maybe a lot of compute happens. And then for other parts of the network, we just recomputing the forward pass when we need to. And just to give an idea how you maybe can reduce when you have a too large network in the end, and then reduce the memory size. We now have a way basically to compute our partial derivatives for all the weights in the network by using backpropagation. Now we have to basically use this to optimize the parameters. And given the partial derivatives, we can now update the parameters. And for this, we are just using, again, the method that we always used before gradient descent. And with gradient descent, we are computing basically the gradient. And for computing the gradients for all the parameters, when we have a very large data set, this is very costly in the end. And it turns out that it's much more efficient if we are just computing of a part of the data, the gradient vector, and then just use this to move in this direction a little bit. And by accumulating these small increments, we are making basically faster progress than by just computing maybe the correct gradient in the end for the whole data set and making a larger step in the end. And therefore, the better idea is to do smaller increments, but maybe more inaccurate increments, but making faster progress in the end. And this comes then down to the concept of stochastic gradient descent, where we have the normal update rule that we are computing the gradients, but now the gradients for a batch. So as noted in the last lecture, we had the convolution, and there we had this so-called batch size. And now it gets maybe a little bit clearer what this is. This is just a subset of all examples. In this case, maybe when we have images, maybe 32, 64, or 128 images for which we are computing the gradient. And then when we have computed the gradient for the batch, we are just updating as before the parameters by going in the negative gradient direction. And as before, the eta is the learning rate, which is a hyperparameter that we have to choose in a way that, that we make fast progress, but as noted before, we maybe don't want to overshoot in the end. So, with stochastic gradient descent, we can already achieve a lot. So we can optimize our parameters, and we can do this in a fast way. But stochastic gradient descent, because of the inaccurate gradient directions, but also in certain situations, we are doing maybe not as much progress as we want to maybe have. In this case, we have here a very narrow cost function. And when we compute the gradient, basically starting as this direction, we are going over in this on the other side of this valley, and then we are just ping-ponging between the different directions here. And in each step, we are not doing basically, we are not making much progress in the right direction, so to say. And this is a problem, but a far more important problem is that our loss function is, of course, a very complex function in the end, or the loss surface is basically a very complex surface. And when we would just do the gradient descent, we have maybe the situation that we are reaching some saddle point where the gradients are almost zero, but it's very flat in the end. And for this, we are maybe want to just get over the saddle point to then reach, hopefully, the global minimum in the end. And therefore, the saddle points can stall the learning progress. And we are now talking about how to improve stochastic gradient descent. So to make faster progress in the end. And the first idea that people introduced was the so-called momentum idea. So for the momentum, we are just accumulating the past updates with a weighted mean of the current of the last update that we did, and sum up the gradient that we compute at that point in time. And then we are just using this updated mean here in the end to update our parameters. And with this, we get the momentum that we are accumulating some speed from before that we can then use to roll over this settle points in the end. So, and this moving average over the past updates allows us then to make hopefully faster progress in the end. So one specific problem when we are now looking at an example, so I will now show on the left side the stochastic gradient descent, and on the right side the stochastic gradient descent with the momentum. As you can see here, the momentum reaches much faster the goal, but it basically also overshoots in this direction. And while it makes here faster progress, it overshoots and then has to go in the opposite direction. And as you can, or as you maybe have also seen from before, we have not only here this overshooting, but it's also then rolling around the minimum here in this case, and therefore, it's maybe a little bit unstable in the end. And to fix this, there was this method proposed, the Nestrov accelerated gradient method, where we just have, so to say, a look ahead. So we are not going just in the direction of the momentum direction, but we are computing basically the gradient at our last momentum direction and look at the gradient at this point. And then using the look ahead direction, we can basically correct for the fact that we are maybe going in the wrong direction. And then by this updating of the gradient direction, we are getting a much better behavior. So, and for accounting for the future change, we can then maybe dampen the overshooting behavior that we had before. So in this case, as you can see, we are not going too much in this direction, and as you can as you also can see here, we are not moving so much around the minimum in the end. And until now, we just use everywhere the same learning rate in the end, but it might be a good idea not to just use it in a way that we apply everywhere the same update, but that we account for the fact that we maybe need different updates for different parameters. And for this purpose, the so-called ADA-grad was proposed, where we are computing just the gradient for the batch, but then accumulate basically the squared gradients in the end here. And using this accumulation, we then scale the learning rate for each of the parameters. So this is really then a vector of the squared contributions of the gradient vector, and by using the division here by the square root of gt, we are then getting a parameter adaptive learning rate in the end. So we are decreasing the learning rate where we have large contributions of the gradient vector, and maybe increasing the learning rate at vectors where it's only very small contributions. So one problem with ADA-grad is that we are just accumulating over time the positive terms here in the end, and with this, because we are dividing here by these positive terms, the learning rate will shrink very much over time. So the longer we train, the smaller will be the updates. And this reaches then the point where we are basically making no progress at all, and do then just small updates with the learning rate again. So, and for this purpose, this was then quickly corrected by other researchers that noted this behavior and then just said, okay, instead of just accumulating the squared gradients in the end, we are just doing a moving average over our last update plus the new update. And with this, we get a much better behavior in the end. And as you can see here, we make fast progress in the beginning, and then we are directly moving in the correct directions because we are now adapting basically for our gradients in x1 and x2 direction, or x and y direction. We are adapting our gradients or the parameter updates in a way, and therefore we are reaching very fast the desired goal in the end and on a direct way. And yeah, RMS-prop is already giving us not this overshooting behavior from before and gets us fast convergence, but maybe has still problems with the saddle points. And therefore, researchers came up with the so-called Adam method, which then combines basically the advantages of RMS-prop and momentum. And this looks a little bit more complicated, but as you can see here, this is the part that we also had before with the RMS-prop. It's just using this parameters beta 2 here. So this is again a moving average over the squared contributions of the gradient. And then we have this MT, which is then basically just the sum over the gradient values, which is basically the same as when we are using the momentum. And this part is just a correction. So in the beginning we have just the mean 0 and the velocity 0, and this means that we are here correcting by this. And important to note is that this is an exponent t. So in the beginning this is 1, or this is 1, and then we have this is increasing. So, and therefore over time, when we did a lot of steps, it's basically just 1 in the end. So in the beginning we are doing a corrected update, and over time we are reducing this update. And then we have the velocity direction mt, and then the vt, which is then the scaling factor. And using both together, so as I said, so it's a combination of momentum and RMS-prop in a way, and using this is very effective in the end. So when we are now comparing here the results of RMS-prop on the left and Adam on the right, then we see that they are both reaching very quickly the desired result, desired minimum in the end. Here in this example, maybe Adam is not having much of the advantage, but as we will see in a short, this is not always the case. So here we have now the question. So we have now this different method. So we have the stochastic gradient descent, the momentum, Nestrov, RMS-prop, and Adam in the end. And the question that naturally arises, which of the different methods I should choose in the end. And to basically solve or maybe provide some insights about this, researchers did an experimental study about the different variants of optimization methods. So far more than we discussed here, but we discussed basically the most important ones, or maybe the progress over for the most important ones. And as it turns out, so here you see different data sets and different networks that were applied. So here convolutional neural networks, but also recursive neural networks, and so on and so on. So for different data set, different networks, the researchers really did a lot of experiments, and it might have also took a lot of time to compute all these numbers. And the important part is here that you can see the curves that basically show the performance. So, and for instance, these CNNs, you want, of course, go in this direction, and I think all the plots are in the direction that the farther the methods are basically on the top. So the interesting part is here the Adam method, so which is the red curve, and you can see that the Adam method is basically always under the top methods, and it's also basically the outcome of the study in the end, that over a large set of experiments we get a good untuned result of the Adam approach in the end. But as it's always like this, it's no free lunch, so there's not a single method that always achieves the best result, but there are in certain situations methods that are getting better or worse. And the suggested receipt of this experimental study is basically, instead of maybe tuning one specific approach, it's maybe better to just use several approaches and then just pick the best from this. So for each of the approaches you have some default parameters like with Adam, and then just choosing from maybe Adam, SPROP, and stochastic gradient descent, the method that works in the end best for your case. So, but in general, also from my experience, the Adam optimizer is very robust and usually performs very well. So for specific data sets, maybe for ImageNet or something like this, where you have a specific training schedule and you have basically a lot of experience also from other researchers, you can just basically use the same receipts there. So usually in the papers there's also written how they optimized it and with which optimizer they used, and you can basically use just the same in this case. But for your own data sets, maybe a good starting point is to use Adam in the end. When we are now talking about the optimization, we also have to talk about the gradients. And in this case, we have basically the problem of vanishing and exploding gradients. So when we are training deep neural networks and we have a lot of these layers, then we have also a lot of multiplications between the gradients in the chain rule in the end. And this can, for instance, for the TAN-H activation, lead to cases where we are reaching points where basically the gradients are getting zero in the end. So at some point in the network, the gradients are maybe saturated in this case, or the function is saturated, and then the gradients is getting zero in the end. And with this, because we have the multiplication, the whole learning dies there. And specifically, this can be a problem when you're not properly initializing your network. When you already initialize the network such that your activations are basically saturated in the end, you will have a hard time to get out of this. And therefore, an important part is to carefully initialize your network. And the second solution to avoid this problem is maybe to try not reach this situation when it's not needed. So therefore, a normalization of the layer outputs. So for talking about initialization, so for the AlexNet, we saw that they just sampled the weight values from a normal distribution, from a Gaussian with zero-centered Gaussian with variance 0.01, and this gave good results. But the important part to note is here that that's maybe not always the best case, because the variance has a large influence on the training. So for this example here, where we have a fully connected network with 10H activations, we can see then maybe this happening. So for the same exact initialization that was used for AlexNet, we are reaching this behavior here. And as you can see here, this is a plot, a histogram over the activations of the TAN-H functions of each layer. So in the beginning, this looks quite good. So we have a histogram of activations that is basically spread over the whole dimension. But as you can see, when you are moving through the layers, this reaches basically a mean of 0 and standard deviation of 0.05 in the end of the activations, which is bad in the end. Because as we are using our activations also to compute in the backward pass our gradients, this will basically be difficult to train this network in the beginning, because we have to correct for this in the end. And the same is happening when we are using the, when we are making the variance too large, then the opposite effect is happening. We are getting basically just activations that are around -1 and 1, which we, when you remember from the graph, are basically the cases where the gradient gets 0. So, and therefore, in this case, we have activations of 0, here we have gradients of 0, and this is the same effect in the end. Our gradients from the layers are getting 0, and therefore we also make no progress. And this will maybe make our training much harder in the beginning. And this effect also occurs, of course, with networks that get bigger and bigger and deeper. So a simple solution is to find basically the variance for initialization that gives us a good starting point for the training, and that also gives us good initializations. And for this was proposed to use as the initialization for the weights, just the 1 over the square root over the number of input dimensions. And in this case, in this example with the fully connected layer, we had input dimensions of 4096. And when we are using this, we are getting then the standard deviation of 0.015. And as you can see here, instead of, so it's a little bit larger than the 0.01, but this already leads to a behavior where we have basically activations that are very well distributed over the whole layers. And important is to note that it basically achieves that the standard deviation of the activations is basically equally distributed over the whole layers. And this gives us a good starting point for the training. When we are not having TAN-H initialization, it turns out that this is not an optimal choice here. So when we have the same, that we are basically initializing now the network with the variance of 0.015, then we can see that basically in later layers we basically get a mean of the activations around 0, and as you remember, 0 means that the gradient also is 0 in the end, and therefore we will have a hard time to get out there. And a better choice for this is to just scale basically the variance by a gain factor. In this case, it's the square root of 2. And with this, we are getting the activations such that the mean is basically around 0.5 and the standard deviation is around 0.0881. And this we can also, this is also implemented then in PyTorch. We can determine these different gain factors basically for different activations, and for several activations, researchers found already a good initial weight. Or a gain factor for getting good initial weights. And using this well initialized initial weights allows us then to make fast progress in the beginning. Or maybe avoid situations like in ReLU where just have situations where we just reach 0 for the gradient and don't make any progress at all there. But still with the activations we have still a problem while training. So it can still happen we have this proper initialization, and then over training it still collapses to this case that we have maybe only 0 activations in the end. And or that our activations are saturated in the end. So, and there the idea is that we include basically the normalization directly into the network and apply this normalizations on the output of the network. And for this, a very influential method was the so-called batch normalization, or is the batch normalization. The batch normalization just computes the mean over a batch of images for each feature dimension. This gives us the mean and the standard deviation as shown here. And using this mean and standard deviation, we can now compute the normalized output vectors. So this is what comes maybe out from the convolutional from the convolutional layer, and then we are applying the mean vector and divided by the square root of the standard deviation, and with this we are then getting the corrected values. And an important part is here that we want to allow the network to also maybe undo these corrections that we are applying, and for this we having these parameters gamma and beta, which are also can be used to maybe shift the mean in the end and also make the standard deviation larger. But it can essentially also learn to just undo the batch normalization. So the problem that you maybe notice is now that via training we have a batch, but when we just want to apply it to a single image, then we cannot compute the batch statistics anymore. And therefore, one idea is to just have a running average over the batch normalizations over time. So, and this is then the thing that we then also store basically in our network. And this is then used at so-called test time. So when we just have one image, we then can compute, we can apply this running averages, and then this will give us the desired batch normalization that we want to apply. And the batch normalization is now included in the network maybe in two ways, or two ways are possible basically. Directly after the convolutional layers and before the activation, so the so-called pre-activation, or directly after the activation, so that we are normalizing basically after the activation, which is called then post-activation in the end. Empirically, there's not so much difference, but what people usually use is basically the pre-activation, so that after the conv layer we are doing the normalization and then apply the ReLU or some other activations in the end. But for different types of networks it might be also advantageous to do the normalization before the post-activation. But this is something that one can try. One specific problem now with batch normalization is that it doesn't work so well with smaller batch sizes. In this case here, this is an image taken from the paper from the group normalization, is when we have a large batch size, then we can reach a validation error that is very low. But when we are decreasing the batch size, so it's flipped here the axis, when we are decreasing the batch size and maybe going to a batch size of 2, then the validation error that we get out for the ImageNet is then very high. And the thing that Wu et al. Proposed here is to do a different normalization. So you can think of, we have now here done, when n is the batch, we are doing the computation of the means over the whole batch. We can also do it, so this is a different way. In the layer norm, we can do it along the layer or for a specific instance. And what the authors of the group norm paper now propose is to do the normalization or the computing of the mean and standard deviation on groups of the layer basically. And using this is then giving us better results in the end. And for certain tasks like detection or something like this, group norm is a viable choice for normalization. So all these things, so using the optimization with ADAM and the initialization, a proper initialization, and using the normalization are ways to get more stable and more reliable learning in the end. And using all these parts basically to get the network learning, we can train basically very deep networks, especially using batch normalization. This is really helping to also get non-vanishing or exploding gradients in the end when we have very, very deep networks. And therefore, when you look in the literature and find different discussion of the networks or the network architectures, batch norm is definitely something that is usually put in. And with this, we are now basically discussed all the parts that are needed basically to get network training. It's the first part was how to compute actually the gradients that we need to update our parameters. The second part was then the optimization. For this we discuss the different variants and the default choice in many, many papers, and also shown empirically that it works very well. It's basically the Adam approach in the end. And for doing then the proper initialization, we had different schemes, but also then for doing the normalization of the output layers to just ensure that the network is trained in a proper way, we use the batch normalization. So, and to summarize, so we had backpropagation for the gradient computation, we had the going beyond gradient descent to actually train networks very fast, and for having a good start for the learning, we had discussed the initialization, and to keep the learning going basically, we had to do some output, the normalization of the layer in the end. And with this, I come to an end, and thank you for your attention and see you next week.